The broadcast is now starting. All attendees are in listen-only mode.
Hi there and welcome from Ventura, California to today's webinar on GNSS and unmanned aerial systems, The Road Ahead, sponsored by Trimble and Inside GNSS and hosted by WebAttract, your end-to-end solution provider for informational webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders as today's webinar is about hearing from these experts as they discuss unmanned aerial systems, the associated concerns, benefits, and their likely expansion into civil applications in the near future. You'll also have the opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with both of our panelists. Now, we've invited you along with over 700 professionals from 59 countries and 42 states and provinces representing a variety of industries and roles. Over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Before we get started, Glenn Gibbons, editor and publisher with Inside GNSS, would like to take a moment to welcome you and to introduce Joe Hutton of Avionics, a Trimble company, and Gnss Degradation, who will be moderating the main portion of today's webinar. Glenn?
Thank you, Roy. Greetings to our global audience from all of us at Inside GNSS Magazine, and welcome to this latest installment in our web seminar series. Today's presentation is sponsored by Trimble and addresses a subject that is generating a lot of activity in the GNSS community, as well as intense interest among a wider audience. That is the design and use of unmanned aerial systems and their probable integration into the national U.S. airspace. Inside GNSS reaches more than 35,000 readers around the world with its print edition and thousands more with our digital magazine and newsletters. And based on the more than 700 registrations for today's webinar, it's clear that UAVs are a subject of considerable interest to our audience. And now I would like to invite Joe Hutton, Director of Airborne Products for the Avionics Corporation, a Trimble company, to say a few words about today's event.
Thank you, Glenn. Welcome, everyone, and thanks for calling in. Trimble is a leading provider of positioning-centric solutions for enhanced productivity, safety, and reduced environmental impact across a number of industries. And we're very pleased to sponsor what we think will be an interesting and hopefully informative session on unmanned systems. There's certainly been a lot of chatter in our industry around unmanned systems, how they will be used in commercial applications, and will they really be as ubiquitous as everyone thinks they will be. So hopefully today we'll hear from our panelists and they'll be able to answer some of these questions and clarify some of this. With that, I would like to thank our panelists in advance for taking the time to share their knowledge with us today.
Thank you, Joe. Our moderator for today's web seminar is Gnss Degradation. Gnss is an assistant professor of aerospace engineering and mechanics at the University of Minnesota, Twin Cities campus. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, Gnss's work has focused on multi-sensor solutions for operations in GNSS-stressed and GNSS-denied environment. Gnss, it's great to have you with us again today. Welcome.
Thank you, Glenn, and welcome everyone, and we're glad you could join us today for this webinar on unmanned aerial systems and the road ahead. The road ahead in part is the challenge of integrating these vehicles safely into the national airspace in the U.S. and the equivalent worldwide. And the challenge is a difficult one, and we don't do it justice in a 90-minute webinar like this one. However, we will try to address two of the key issues here, which is the integration and certification issues associated with using these vehicles. Before I introduce the panelists, however, I'd like to take a few minutes and kind of frame the webinar for today, and that way I'll set definitions and terms that we'll use for this webinar. And we'll do that by starting first by a quick poll that will give us a pulse of the audience. So, Lori, if you could set that poll.
Absolutely, Gnss. And folks, you should see up on your screen our first poll. And we'd like to know, what do you see as the single biggest civilian application for unmanned aerial or ground vehicles? And if you would, go ahead and just select one. of the following choices: environmental monitoring and management, agriculture, for example, crop dusting, crop monitoring, autonomous cargo shipments, search and rescue or medevac operations, or mapping and survey. And let's go ahead and take a look. Demos, how do those stack up?
Well, kind of as expected. There's a lot of mapping and surveying applications that are going to be coming along with these vehicles, and overall looks good. The point of that poll was to dispel the myth that UAVs are primarily for military and law enforcement applications. There's a lot of civilian applications that could benefit from them, and as shown on the slide, I have two examples of that. On the left, I have a Global Hawk, which you're seeing here is the civilian version of it used by NASA for gathering data for atmospheric and weather monitoring. And on the right, you have a small hand-launched UAV ATI resolution, which is used for monitoring of ocean surfaces for debris and nets and things like that. So the civilian applications for these vehicles is quite diverse, and the vehicles that can be used for these applications range in size and from large to very small. However, the common challenge that we need to address before we use them is how do we share the same airspace with manned vehicles, with manned aircraft with these vehicles. And that's kind of the theme of today's webinar. You may see this video that's coming on maybe a little bit choppy as it comes along, but what it shows is that there's, again, as I pointed out, that there's very different capabilities in the UAVs. The one on the Global Hawk on the left requires a runway for landing and takeoff. The small hand-launched ones require, well, they're launched by hand and they land on, in this case, in water. So even though they're very different, the basic challenge that we need to answer and that we need to address here is how to share the airspace with other manned aircraft. And to put everything in context, here's a quick diagram to keep in mind, which basically shows the systems on board most UAVs. They're all not going to be the same, but they're going to be fairly similar to this. And on the airborne side of the house, what we have is a control system, a navigation system, and a guidance system. The navigation system tells the vehicle where it is. The guidance system takes instructions from the ground operator, shown here, and compares that to where the navigation system tells the vehicle is, and generates a path in the sky that the vehicle should follow. And that information is then sent to the control system, which actuates controls to guide the vehicle to carry out the intended function that's being commanded by the ground operator. The vehicle and the entire ground system and data links together are normally called a UAS. So when we talk about these vehicles, we need to include the entire system, just not the aircraft itself, but also what's on the ground. Now, there are a couple of challenges, and I'll kind of focus on three of them. And the first one has to do with the fact that most of these small vehicles, and we'll focus on the small ones somewhat in this webinar, rely on GPS and GNSS as the key sensor for position, velocity, and attitude determination. If GPS or GNSS goes away, as it can when we have a jammer, as shown in this diagram, that completely denies GPS, the brown region here, or stresses it, where the signal quality degrades, then the position and velocity solution more or less goes away on these small unmanned aerial vehicles. So the question is, how do we deal with that kind of an outage? The attitude solution also tends to go away, but there are ways of dealing with that. But again, GPS is key, and how do we deal with that is one of the big challenges. While there are solutions in the form of some of the ideas being pursued by FAA and the APNT effort, those are suitable for large UAVs, but not for small ones. So that's one challenge, and you'll hear more about it from one of our panelists today. The second challenge, or one of the challenges, is the problem of the sense and avoid problem. And in effect, this problem is basically how does a vehicle sense the environment around it and avoid running into other vehicles in the sky. The way it's done currently, at least with manned vehicles, depends on whether or not you're flying under visual flight rules or IFR, or instrument flight rules. In the case of IFR rules, you have 5 layers of defense that ensure, or more, that ensure that you don't run into other vehicles. Their airspace, procedure, radar, and things like TCAS and cockpit display of traffic information. And at the last layer, you have the pilot's eye. In the case of VFR conditions, you have 2 layers of defense. You have procedures, and then you have the pilot's eye. The question is, with the UAVs, is where do they fit in? Are they going to be as IFR, or is it going to be as VFR? And if as VFR, what's going to replace the pilot's eyes? What kind of sensors do we use in that kind of a condition? So that's a significant challenge that has to be addressed before these vehicles can be used safely in civil applications. A third challenge has to do with reliability. And the consequence of system malfunction on these vehicles can be severe. The small ones maybe not, but the large ones, it can be pretty severe. So how do we make sure that system failures, be it hardware or software, does not cause problems? And the traditional way to do it in aerospace is by adding redundancy. So everything has two or more of its copies. If one fails, the other one kicks in and backs up. While that works fine for large UAVs, it's not really going to be a solution for small UAVs because size, weight, and power, SWAP, as it's called, is a big constraint. So we can't put redundant systems on these vehicles. So how do we deal with redundancy and reliability? One of the approaches that's being looked at, and it's kind of a focus of some of the work we're doing at the University of Minnesota, is to look at analytical redundancy, which is basically software that's smart and algorithms that are smart to make up for the lack of redundancy in hardware. So these are some of the issues that we're going to have to deal with. So our panelists today will address both of these, will look at some of these issues, and will give us their insights as to what the issues are. So with that, let me go ahead and introduce our first panelist. Our first panelist is Josh Redding, who is currently a research lead at the Lockheed Martin Proceres Technologies, a developer of the Kestrel Autopilot system, where he works with vision-aided guidance algorithms for vertical takeoff and landing aircraft and various other approaches for payload-directed UAV guidance and navigation. Josh has over 10 years of experience in the area of guidance, navigation, and control and the autonomy of manned systems, and he holds a PhD in aeronautics and astronautics from the Massachusetts Institute of Technology. Josh?
Thanks, Demos. Appreciate it. Okay, so Demos gave you a really good overview of what exactly a small unmanned aerial system is. So what I'm going to do first here is just take a few minutes and go over that system in a little more detail. So here on the slide, what we have is a Raven UAV, and I just wanted to talk briefly about what constitutes an SUAS. What is the architecture of a small unmanned aerial system? For starters, we've got this. It starts out with an airframe, such as the Raven, something that flies, something that goes up in the air. On board, you've got Autopilot and Avionics. You've got some kind of power system, provides propulsion, some kind of communication system to link up with the ground control station here, and some kind of payload. The payload can be a number of different things, and we'll talk about that in a minute. The actual aircraft itself, they can range, as Demos mentioned, in size from the Global Hawk, which is huge, down to something that's fits in the palm of your hand. When we're talking about SUAS, the small unmanned aerial systems, we're typically talking about systems, airframes that are 1 or 2 man packable, they're battery powered, they're hand launched, and they're are on the range of under 20 pounds. Now that's not set in stone. That's just on the order of under 20 pounds. In these pictures here, you can see a handful of examples of these types of systems. As far as communication system goes, and a data link with the ground control station, the GCS, this provides command and control from the operator to the UAV in the air. It also provides the data downlink from the UAV and data logging capabilities on the ground on the GCS. It also often provides some kind of streaming video or some kind of data downlink that you can then exploit. The reason that these things are in the air is to gather some kind of data, and that communication link provides you with real-time access to that data, which is the reason you're flying in the first place. Now, these communication systems, there's a picture of one here in the lower right-hand corner. They're very small, they're very lightweight, and there's competing objectives here because you need them to be low power so they don't consume all your battery, but you also want a long range, which requires more power. So, I mean, this is just one example here, but there's a quarter there next to it as far as sizing goes. Now, payloads, so just about anything you can think of that you want, any kind of sensor you want, there is a payload associated with that can be flown. Typically, currently, I should say, a lot of these payloads are just camera systems, basic off-the-shelf EO cameras like your Pentax or your Nikon DSLR or whatever. There are also a growing number of infrared cameras on board these aircraft, and in particular in the agricultural and mapping areas, these multispectral and also hyperspectral cameras here are also common payloads. Gimbaled payload systems, such as this one from UAV Vision and this one from Brandenburg Tool, enable the camera to be pointed just about anywhere you want while the plane is flying its path. So again, these payloads are really the reason we're flying these small unmanned aerial systems. The reason why we have these things up in the air is we want to get some data somewhere that would be otherwise too expensive to get, or that it just makes a lot more sense to have it automated. For example, here, this multi-ray sensor, pollution weather sensors such as this, or chemical sniffers such as this, or synthetic aperture radar such as this. These things are all coming down in size, weight, and power, as Demos mentioned, the SWaP criteria, all within the realm of feasible payloads on board an SUAS. So then we focus a little more on the autopilot here. The autopilot is really the brains of the whole system. And in these small systems, the autopilot is really the only thing on board that controls. I mean, it's really the only computer on board. It controls everything. Now, in these bigger systems, like the Global Hawk, the functions of the autopilot are split into multiple modules that are separated. Now, we don't have that luxury on small unmanned aerial systems. That all kind of gets combined into one unit, like this pictured up here in the upper right-hand corner. Typically, you've got some kind of microcontroller or some kind of CPU that then connects with all your sensor arrays and your communication module. And on board this little computer is running a handful of control loops, the guidance, the navigation, the control, kind of the GNC algorithms that the Demos talked about earlier. We're also linking to some external sensors, possibly, such as these ones shown here, this little IMU, inertial measurement unit, which gives you, typically what this gives you is angular rates and body accelerations. So that kind of, they can give you relative motion measurements as to, okay, am I pitching to the left? Am I rolling to the left? Am I pitching up? Am I falling? Those kinds of things are what these kinds of sensors can give you. Now, in the autopilot, in the upper right-hand corner, those sensors are built in right here in the upper left-hand corner of the autopilot there. So they're not always a separate board or separate sensor. They can be integrated in on the same board. Now, GPS, or GNSS, I guess, more generally. This, as Demos mentioned earlier, this is a key position and velocity sensor for your autopilot. There's really nothing that compares as far as size, weight, and power that can give you such great information. So moving then to the firmware, or the software that sits on board the little embedded system, or the microcontroller. There's typically a handful of loops, your guidance, navigation, and control loops. As Demos mentioned earlier, your navigation solution is typically what gives you your exact location. Tells you where you are, tells you what your attitude is. It's kind of like your state vector, if you're familiar with that term. That gives you a snapshot of where your current location and orientation. You also can have a goal location and orientation associated with that loop. Now your guidance loops then the purpose of them is to generate a trajectory to go from your current location and orientation to your goal location and orientation. Now, as Demos mentioned earlier, that goal location often comes from the operator in terms of a waypoint or a waypoint coupled with an attitude, those kinds of things. And I guess finally there, the third bullet under that GNC is your control loop. In your control loop, really all you're doing is generating the actuation commands like your elevator, your rudder, your aileron deflections necessary to give you the proper forces and moments on your airframe that will then enable your airframe to follow its desired trajectory. So those are the three main kind of low-level loops in the firmware going on board just about every autopilot that I know of. So then you've got on top of that your payload interaction. So like we said earlier, the payload is really the reason why you're flying. So you really want that payload tightly integrated with your autopilot. And so you've got some loops running on board your autopilot that kind of manage and babysit your payload. They take into account user inputs or operator inputs. Say the operator wants to look at something else, then that input gets sent up from the ground control station to the autopilot. Autopilot interprets that and then passes that to the payload, where then the camera can be gimbaled or so forth. You can trigger a snapshot. You can begin collecting data. You can stop collecting data. You can average the data. You can change the parameters of the filter you're using for the data. These kinds of things. Now, one of the key things, at least that I think, is that this payload, the data you're receiving from the payload, can and often needs to influence your GNC algorithms. For example, vision-aided or vision-guided navigation, or if you're following a chemical trail, you need to close the loop around the data received from your payload. And finally, communication. If for this mission to be useful, this isn't always the case. You can post-process, but typically what you want is a live downlink from your vehicle, from your payload down to the ground control station. So you can receive and process commands. You can change the controller. You can change flight modes from hover to forward flight or to loiter. And you can regulate and monitor your telemetry that's being downlinked. Okay, so that's kind of a generic overview of what an SUAS is, or what SUAS are. Now let's talk a little bit about some of the subsystems that make them up, and I guess I'm arguing here that SUAS are complex systems of systems. So for starters here, you have very significant size, weight, and power restrictions, and because of those things, we don't really have the budget for physical redundancy. You can't have 2 wing servos on there, 2 aileron servos. There's just not enough. You don't have enough payload. To put another servo on, you have to take from your usable payload. That's not something that most people would be willing to do. And also, these swap restrictions lead to hobby-grade hardware. That's not to say that the hobby-grade hardware is not good and not reliable. It's just these things have not gone through the testing that, say, an accelerometer inside your automobile has gone through, or some component of your car, or some component of the Dreamliner, for example, has gone through. These are hobby-grade servos, hobby-grade speed controllers, and hobby-grade sensors that, that by and large work, but have not gone through the reliability testing of other more expensive, heavier solutions. So typically, your airframes are all fly-by-wire. You've got microcontrollers for nearly every subsystem. For example, inside your servo, there's a little microcontroller. On board your ESC, there's a microcontroller. And your GNSS receiver, there's a microcontroller. Each of these things have their own set of firmware, their own configuration files. And these things all have to they all have to work independent and in cooperation with each other. Another challenge is just the RF environment on board these small unmanned aerial systems. I mean, we're talking things that are a couple feet wingspan, 2, maybe 3 feet, maybe 1 foot wingspan. And on board, you have to have a GPS receiver. You have to have some kind of modem, some kind of radio modem that emits a lot of RF noise. And these things are by necessity very close to each other, which results in a very noisy, compacted RF environment. Okay, so lastly, I guess what we really need for SUAS to operate in the national airspace, they need to be reliable and predictable. Now, this behavior, reliability, and predictability, it really depends on all of these subsystems working independently and, more importantly, in harmony with each other. Now, there are a lot of solutions for when things, when things like this, when something fails, when a subsystem or component fails, there's a system in place on nearly every autopilot that I know of that are called Failsafe Behaviors. So these are things typically in software. This goes along the lines of analytical redundancy that Gnss was talking about, where what happens if? So the first one, what happens if there's a mechanical or firmware issue? Now there are a lot of things that can be done, and Gnss lab in particular has done some work here in the firmware issues. And also, what do you do if you lose communication link with your ground station? What should the airplane do? Or what should your UAV do? Or what should your UAV do if there's a loss of GPS signal? Or if it's degraded such that it becomes unusable? Typically, the SUAS or the UAVs, I guess, can maintain their attitude in the event of loss of GPS, but they drift in absolute position, and because of that drift, their behavior becomes unreliable and unpredictable. And I guess that was just a quick overview of some of the aspects of an SUAS, and with that, I'll turn it back over to you, Demos.
Thanks, Josh. All right, so next I will introduce Kelly Hairhurst, who is our second panelist. And Kelly is a senior research scientist at NASA Langley's Research Center in Hampton, Virginia. She holds a BA in mathematics from Virginia Tech and an MA in mathematics and operations research from the College of William and Mary. Since 1988, she has worked with the FAA on numerous research projects involving verification and certification issues for aviation software. And she has participated on RTCA Special Committee 190 and 205 on aeronautical software standards, and is currently a member of the joint RTCA EuroK forum on aeronautical software. Ms. Hairhurst currently serves as a subject matter expert on software and safety assurance as part of NASA's Unmanned Aircraft System Integration into the National Airspace System Project. Kelly?
Thank you, Demos. Hi, I'm Kelly, and I'll start discussion of integration with just a high-level overview of regulatory and research activities. You often hear the FAA talk about UAS integration in 3 phases. Phase 1 is the accommodation phase, and that's where we are today. In this phase, the FAA is using existing regulations and guidelines along with special mitigations and procedures to allow some access to the NAS on a case-by-case basis. And as you might guess, that's not very efficient, but it's a start. The second phase is the integration phase, and that's where the FAA will establish UAS certification criteria, performance requirements and standards, the things needed for more routine access to the NAS. For example, the FAA is working on a small UAS rule to increase access in the near term, which will be a really good step toward integration. And the final phase of integration is the evolution phase. And in this phase, the FAA will establish the policy, regulation, procedures, and so forth to enable routine NAS access in a next-gen environment. So let's look at operations today. UAS are operating, but access is really very controlled and, as I mentioned, granted on a case-by-case basis. And there are basically 2 types of operations allowed. The first is by public aircraft, which are aircraft operated by the government. That includes the Department of Defense and Homeland Security, of course, but it also includes entities like NASA, state universities, and law enforcement. They operate for public use. And public use aircraft can operate today under a COA, which is a Certificate of Authorization or Waiver. And this chart shows the number of COAs that the FAA has issued over the past few years. So we have quite a few operating. Now, civil aircraft, on the other hand, they're essentially any aircraft other than public use or model aircraft. And civil aircraft can operate today, but only under a special airworthiness certificate in the experimental category, which comes with a lot of restrictions. And a primary restriction, probably of interest to a lot of you, is that no commercial operations are allowed by the FAA at this time. But times are changing. As many of you know, Congress has stepped in to require the FAA to facilitate much wider domestic operation of unmanned aircraft than is currently possible today. And those requirements are in what was called the FAA Modernization and Reform Act of 2012. And that act includes a requirement that the FAA produce a plan and a roadmap to accelerate integration for civil use. It requires the FAA to issue a final rule to allow some civil operation of small UAS. And then this next one, this is a big one. The FAA is charged with establishing 6 test ranges for UAS. Just last month, the FAA released a screening information request, which is similar to a request for proposals, soliciting information from interested parties. and there's a lot of interested parties in this. Next is a directive to designate permanent areas in the Arctic where small unmanned aircraft can operate for 24 hours a day for research and commercial purposes, with those operations being beyond line of sight. And finally, the FAA is charged with improving the COA process for public aircraft. So the FAA has a lot on their plate, and they're working on it. The FAA's released a concept of operations document for UAS, and they're working on a roadmap in addition to actively working on improving their COA process. The FAA has established an ARC, which is an Aviation Rulemaking Committee on UAS that's actively working to provide recommendations for means to continue integration effort. Then there's the JPDO, which is the Joint Program Development Office. They're putting out their own UAS national roadmap. I guess folks think we need a lot of navigational systems here in the UAS world because we have a lot of roadmaps coming out. Next is the RTCA, which is a standards organization. They have a special committee, number 203, which has been working on minimum operational performance standards and minimum aviation system performance standards for command and communication systems and sense and avoid systems. And then finally, there's lots of research activities in government organizations, including the FAA and NASA, and I suspect in many of your own organizations too. And that's just really a peek at some of the current activities. So let's take a look now at some of the challenges from a regulatory perspective. This diagram represents integration challenges with respect to people, aircraft, and operations. First off, the people part, and specifically qualification standards for unmanned aircraft pilots. There are a lot of different schools of thought on that topic, and we're not going to go there. We're going to go to aircraft and systems. That's a better place to go. And we have some significant technical challenges here. Reliability is a big challenge, especially for smaller systems that don't want the weight penalty of redundant systems. And you heard both Demos and Josh speak to that. Next is understanding certification requirements for the overall system, as well as components such as the ground station, the control links. All of that is still to be determined. Having radio frequency bands dedicated and secure for UAS communication and control is absolutely critical, as is having a sense and avoid system that can take the place of an onboard pilot's ability to keep a safe distance from other aircraft and obstacles. And then finally, there's the operational challenges with respect to interoperability with air traffic control and all of the operational changes coming with NextGen. So there's clearly a lot of work to be done, and we at NASA are trying to help out with that. We're here to help. So about 2 years ago, NASA established a new UAS integration in the NAS project. This is about a 5-year, $150 million project working on some of the technology challenges. And one of the key aspects of this project is that the technology development we do will be tested in a high-fidelity test environment. This project is led by Chuck Johnson out of NASA's Dryden Flight Research Center that specializes in flight test technology and demonstrations. In fact, Dryden just put out a video that shows some of their unmanned aircraft assets, and it's pretty cool. So they are well versed in doing some extraordinary flight testing work. And our project, it's divided into 5 main focal areas. Those are communications, separation assurance, sense and avoid interoperability, human systems integration, certification, and integrated test and evaluation. And notionally, our 3 technology pieces work towards resolving airspace integration issues, as well as standards issues for those technologies. And then the test and certification parts are really ancillary to the technology bits, but really important too. And just a few more notes on what these technology pieces do. Our communication work is focused on effort to get appropriate radio frequency spectrum allocated for UAS, and they're also working on building a prototype radio that goes with that. Our SSI work is assessing the interoperability of UAS sense and avoid systems with the Gnss and investigating the effects of mission and performance characteristics and communication latencies on separation roles and responsibilities. And our HSI work is studying human factors issues in ground control stations, and they're also developing a proof of concept ground control station. And the artifacts from these three efforts will be tested in a number of integrated events. So that covers 4 of our 5 areas, and I've saved the best one for last, and that's our research and certification. Now, don't be alarmed. Certification, that's actually good stuff. And I think it's important to say that certification, it really means different things to different people. The FAA certifies a lot of different aspects of the aviation system, including aircraft and aircraft components, the ability of an aircraft to comply with airspace and operational requirements, and they also certify or license people involved in our aviation system. And the research we're doing as part of our certification sub-project is focused primarily on airworthiness certification of UAS. And we'll talk about that in a few more minutes. So back to you, Demos.
Thank you, Kelly. All right, so at this time we'll take a pause to open the floor for questions and answers for the audience to ask the panelists. And in addition to Josh and Kelly, we also have Joe Hutton and Norse from Trimble that will be willing to field some questions. All right, so with that, let's see. The first question is, it's going to be a question for Joe, and it's from Brad, and it says, basically it's with respect to aerial survey applications with the objective of surveying spatial data, are you aware of any measurement uncertainty analysis performed on such systems, or in plain language, how accurate can you survey with a SUAS or UAS in general?
Well, I would almost categorize that as two questions. So if we look at the latter part, how accurate can you survey with a UAS? From our perspective, a UAS is really just another aerial platform. In other words, what people have been doing the last 20 years from manned platforms can apply to unmanned platforms. The fundamental difference, of course, is usually size, weight, and power. But all that technology that's gone into these mapping systems and the accuracy that are getting on the manned platform can be achieved from unmanned platforms. It's just a little more challenging because of the swap issues that were brought up already. However, one of the advantages that a UAS has is that it can get lower, and it can do things a little slower. Those can actually translate into higher accuracy. If you think of it, a small unmanned system that can fly very low can essentially do close-range photogrammetry like you would do from the ground. So in plain language, the accuracy of these things will be as good as what you're getting from manned platforms. In terms of any studies, yes, there's been a whole bunch of analysis been done, both for manned platforms and unmanned platforms. Trimble has a product called Gatewing that has done an analysis. It's a UAV turnkey system for surveying and mapping. And I would encourage anyone, if they want to talk to the folks from there, they can give you a whole analysis of what kind of accuracy they can get from a small UAS.
Right. Thank you, Joe. Next question is from Robert, and I guess this will be for you, Josh. And it's basically asking a question is, how do you, in your autopilots or in your avionics, is there a way to deal with engine failures? Is there some standard way that we're looking at that?
Sure, yeah. So I don't know that there's a standard way necessarily to deal with engine failures. The bottom line is you lose an engine, you're coming down. There's really no other way to stay in the air without your propeller comes off, your engine seizes, your ESC just stops working. But what we can do is you can maintain what the autopilot does in almost every case is we'll make sure that the airplane doesn't stall. And what it'll do then is it'll drive a pitch from airspeed control loop. So that in other words, if it starts to get low on airspeed, it's going to pitch down so that it maintains enough airspeed so that it doesn't stall and fall out of the sky. Now, when that happens, if it's the kind of thing where you can detect that engine failure, and you often can, then your failsafe will kick in and try and bring you as close to home or as close to some predetermined waypoint as possible. And I think that's a pretty common method for dealing with engine failures that are detectable.
All right, thanks, Josh. All right, let's see. This one is from Rick, and it's going to be for Kelly, and it's more a question on qualification. The question is, do state government operations fall under designation as public government for the way things are working right now?
Oh, yay, an easy question. Because it's yes. Any government operation of an aircraft is considered to be public use. So there you go.
All right. Let's see here. Yeah, the next one. Again, this one, you know, I'll pose it to you, Kelly, but I'm not sure how far I guess the work has gone, but we'll try to answer it. And it's from Logan. Is there any discussion right now on the details of any of these test ranges? In particular, is there any talk about how GPS jammers might be integrated into testing out avionics in these places, or is that too early to be even talking about at this point?
At least as far as I'm aware, I think it's a little early to be talking about that. I'm not in the inner circles of the FAA or anything like that. I think the idea is really interesting, but I'm not aware of any specific discussion about that.
Okay, thank you. All right, we have lots of questions, and we'll try to get back to you later on if we can, but for the sake of time, we need to get back to the second half of our panel discussion. So let's move on to the next part of it, and we'll do that by starting with a poll. Lori?
Sure, Demos. Other than regulations, what is the top technical issue currently limiting the use of unmanned vehicles for commercial applications? And again, we'll ask that you select one. Is it endurance of battery and power plants? Is it reliability and safety of systems? Is it GNC, guidance, navigation, and control system performance? Sense and avoid capability? Or maybe you think it's something else, an other. If you do select other, we'd love to hear your input, and you can go ahead and put it through the question pane and tell us what you're thinking. Got Kevin saying startup costs, John, privacy concerns. There you go, Demos. Any thoughts?
Well, it looks like it's an even spread between power, reliability, and sense and avoid capability. All of those are important, but one of the big things that's going to be important, obviously, is certification. And the next half of this panel discussion will be on that issue. So let's go on to that. All right, so I'll hand it over to Kelly for discussions on that. Kelly?
All righty, thank you. Before we dive specifically into airworthiness, I think it's a good idea to get a high-level notion of the context for our discussion. And that context is really provided by the Federal Aviation Regulations. And the FARs provide rules and standards for aircraft, operations and infrastructure like airports, and people involved in the aviation system. And the FARs are generally the starting point for other forms of policy and guidance material. And airworthiness, as you might expect, falls under rules for aircraft and certification. And there's actually 3 certificates related to this. One is a type certificate that indicates that the particular design of an aircraft complies with its designated safety requirements and standards. That is, it's designed so that it can fly safely. Next is the production certificate, and that indicates that manufacturing has sufficient quality control to faithfully produce the approved type design. And then there's the airworthiness certificate, and that indicates that an aircraft, as built, complies with its type design and is in a condition for safe flight. Now, inquiry minds want to know what airworthiness requirements should there be for UAS and their constituent components so that manufacturers know how to design and build their systems and components to meet those requirements. So, what exactly is airworthiness? Well, airworthiness in general means the ability to operate without significant hazard to air crew, ground crew, passengers, or to the general public over which any airborne system is flown. And there are 5 main sets of airworthiness standards in the force today. Part 23 covers smaller manned airplanes, general aviation airplanes up to commuter aircraft with 19 seats or less. Part 25 covers large transport category airplanes. Part 27 is for normal rotorcraft. Part 29 is for large rotorcraft. And then there's Part 31 for balloons, which are really fascinating but not so relevant. And the airworthiness standards for all of these things, they tend to follow the same basic format. That is, there's rules for structure, design and construction, power plants, which are the stuff necessary for propulsion, including fuel. Avionics requirements typically fall under systems and equipment. We have lots of existing standards, and the million-dollar question is, do the existing standards, that is what's in parts 23, 25, 27, and 29, do they apply to UAS? Do all of the standards apply? Well, probably not the ones regarding seat belts or lavatories, but do some of them apply? Do they apply to all UAS, regardless of how big or how small, or regardless of what they do and what their mission is? And then what about standards for those parts that aren't part of a conventional aircraft, like the radio control links, ground control stations, launch and recovery equipment? We might need some guidance for those things too. So how do you know what of these standards might apply to your aircraft or for particular equipment you're building for an aircraft, like the navigation systems, things like ADS-B, sense and avoid systems similar to TCAS or Autopilots? What do you need to know to design your system or equipment to meet airworthiness requirements? To answer that, we're going to look real fast at a particular regulation that I'm going to call a .1309 regulation for short. And that's where we learn a lot about what applies to avionics. All of the airworthiness standards have a .1309 regulation for systems and equipment that essentially says that the intended function of all systems must be performed under any foreseeable operating condition. That is, your system has to do what it was designed to do, and that makes sense. And the tricky part, it's the second half, and that is that unintended functions must be improbable. And things that prevent safe flight and landing must be extremely improbable. Essentially, you don't want bad things to happen. And I know I don't want bad things to happen when I fly. So this all boils down pragmatically to reliability requirements, which impacts the needs for redundancy that Josh and Demos talked about, and also require design assurance levels for software and complex electronic hardware. And here's an example of what those look like for Part 25 airplanes. Large passenger airplanes must be designed so that the probability of a single component failure causing a minor hazard is 10 to the -5, and the software must be developed to meet Level D objectives in a standards document called DO-178B, or what's soon to be Rev C of that document. And as the consequence of failure increases, so do the reliability requirements and the rigor with which software is developed. And that makes sense, certainly with people on board an aircraft. Our million-dollar question would ask, would these requirements apply to a large UAS, say one that weighs more than 19,000 pounds? And would the safety critical software have to be developed to comply with level A requirements? And then how does it look for smaller UAS? Well, this next chart simply shows how different categories of existing aircraft map to different specifications of reliability and design assurance requirements. And one thing to notice about this chart is the fairly large weight range for each category. And that's important, especially if a decision is made to apply these categories and corresponding reliability requirements to unmanned aircraft. For example, if these categories were adopted by the FAA, then an unmanned rotorcraft weighing, let's say, 75 pounds would have the same reliability and design assurance requirements under a standard airworthiness certificate as one that weighs 6,900 pounds. Now, that's something to think about. And that's exactly the things we're thinking about as part of our NASA research into certification issues. When you start thinking about how different unmanned aircraft of extremely different sizes and weights and missions, how those should map to reliability and design assurance requirements, it's helpful to keep a fundamental principle in mind, and that is aircraft with similar risk should be held to a similar standard. Aircraft that pose a lot of risk should be held to a higher standard than those that don't, and aircraft that don't pose a lot of risk should not be unnecessarily burdened. So the research we've been doing for the past 2 years is looking at how to characterize risk for unmanned aircraft and operations so that unmanned aircraft that pose similar risk can be grouped together. And that's what I get to do for fun. And there are two main parts of our research. Part one is looking at the different factors we think and that others think influence risk related to airworthiness. And the other part of our project is collecting hazard and risk-related data on unmanned aircraft, especially from NASA. NASA uses a number of different unmanned aircraft in our science missions, and many of you may not have known that, although Demo showed a picture of our Global Hawk earlier. And we want to be able to learn from failures and incidents and accidents to help us better understand risk. And that's what we're working on, and it's very much a work in progress. And just to close, I think it's really important to remember that airworthiness standards for unmanned aircraft are still being debated. Coming up with appropriate standards is not easy, and it's not likely to happen soon. A key to getting those standards right is understanding risk associated with safe flight and operation of UAS so that those risks are abated through appropriate design and operational mitigations. And it's our job at NASA to simply help provide data to contribute to that understanding. So with that, it's back over to you, Demos.
Thank you, Kelly. All right, so I'll hand it over to Josh here to talk about, again, looking at the issues associated with avionics to put SUAS in the NAS. All right, it's yours, Josh.
Okay, thanks, Demos. Okay, so thanks, Kelly, for painting that picture for us. So what I'm going to talk about here is how to get these SUAS to fit into the national airspace. Now, speaking from an SUAS developer's perspective, we definitely want SUAS in the NAS. As one who sells these things, the more people who buy them, the better, right? I mean, so we want to cooperate in all the ways that we can. At the same time, we want to make sure, as Kelly mentioned, that we're not unduly burdened with these really restrictive limitations and regulations for something that weighs like 20 pounds and it may not pose much of a risk at all. So because the FAA will require reliability and predictability, what are the things that SUAS developers can do to ensure that? Well, a lot of these things we can do, for example, in terms of fail-safes, in terms of making sure that our software is designed in such a way that if we lose a sensor or if some mechanical failure happens or if GPS is degraded to the point where it's unusable, what happens? Now, we need to verify those in terms of this document that Kelly mentioned, this DO 178B or C, where we can prove that our software, our firmware, is reliable to the point where we can get to these 10 to the -5th failure rates, really, really small numbers. Now, currently there is really only one metric for determining how reliable an autopilot is, and that's really its flight hours. There currently isn't any FAA stamp that you can get on your autopilot that says this autopilot is certified to be awesome, or anything like that. What you really can tout is how many flight hours do you have on the system, and how many varieties of situations has the system performed. Out of how many of these hours, how many systems have you lost? Those kinds of things. So, for example, the Kestrel autopilot produced here at Lockheed, we've got about 15,000 flight hours on the Kestrel system. Now, the in situ Scan Eagle has about 600,000 flight hours on their system. And this is kind of what we're going for, what SUS developers in general they're going for. They need to bump up those numbers to lend credibility to their product. Okay, so dealing with GNSS degradation. So as we mentioned before, GNSS or GPS is a key sensor in SUAS and UAS in general, and aviation in general. So dealing with the degradation is a major issue. Now, what happens when your GPS degrades or you lose it altogether is you end up getting this positional drift in your vehicle that's undetectable by your IMU. So your vehicle is drifting in ways that it does not know, and therefore its location becomes unpredictable and becomes unreliable. Now, some of the things that the FAA is looking into, and I believe also NASA is looking into, and also universities like Stanford, for example, looking into how can we locate a vehicle in the absence of the GNSS. So a lot of these systems, well, they're in general aviation, some of these systems currently exist, like VOR radials, things like that, things where you can measure your distance from a known airport in general aviation. Now, these things require often large in an SUAS perspective, sensors to be placed on board, things that simply would not work for the scale of systems that would classify as a small unmanned aerial system. So one of the things that this the alternate position navigation and time proposal by the FAA proposes is to use these things called pseudolights, for example, as one particular instance, where you've got these ground-based emitters that then locate an airplane and send up in a signal similar to GPS. It's essentially ground-based GPS, so that the airplane can then locate itself using these signals instead of a GPS signal. Now, that requires infrastructure. Infrastructure is expensive, but that is definitely a possibility where the onboard requirement for SUAS is minimal. Okay, so then there's the sense and avoid issue. Well, so this one, I think just about any small unmanned aerial system developer would argue the necessity of such a system on such a small platform. Now, vision and sensing capabilities are extremely important and extremely useful. For example, we've got this little video here I can show you of some work we did here at Lockheed with vision-aided landing. What you see in the video is a screenshot of a ground control station with a live video stream from one of our aircraft. The user here is clicking on this little pallet, which is on the corner of a roof, and then he's going to go over here and click land. And so basically what will happen is the vehicle will then use its camera position information and the location of that object in the video feed to navigate around. And so it's going to just go towards that pallet and land. This is a very basic implementation of kind of vision-aided or sense, and in this case not really avoid, but more attract, an application of this. Now, if you don't have, so sense and avoid becomes trickier. So if you have GPS or GNSS that's available, sense and avoid can be handled pretty effectively with things like ADS-B, in and out, or computer vision, such as what you're seeing here in the video. Without GNSS, however, it becomes a little more complicated in the sense that you really need to have either radar on board or some very comprehensive vision solution where you get a much wider field of view than a single camera, or you have a ground-based solution, which in general aviation is similar to the Mode C transponder. So while Kelly talked about public and civil use of UAS in the national airspace, as a developer, we're excited for this. We're pushing that forward. We're also pushing commercial acceptance, which is not currently, there's really no roadmap yet for commercial integration to the national airspace. So as a result, kind of we're looking towards the civil application where you need to have an airworthiness certificate that Kelly talked about. And the implication for the SUAS developer or even manufacturer or purveyor, so to speak, would be they need to, you're going to see these types of people really assisting their customers in obtaining the proper authorization. They're not going to sell you a system and then say, you know, goodbye, you're on your own learning how to fly it and obtaining proper authorization to fly it. And in conjunction with that, you're going to see a lot of these SUAS developers and manufacturers trying to get in on feeder panels and work groups with the FAA to try and help them define that certification process so that we can, well, this is, you know, fairly selfish, I suppose, but so that we can make sure that the regulations imposed on small unmanned aircraft are not the same as those regulations imposed on ones that, you know, weigh 36,000 pounds and, you know, pose a serious threat to anything they're flying over. Some other implications for developers. So the bottom line is we need to guarantee reliability and predictability. In a lot of cases, we can do that currently. Transponders, SUAS can support those. There's a current transponder on the market now that's about 100 grams. We can integrate that. We have that kind of payload. Now, anything that's bigger than that, there starts to be a question mark there. Can we integrate that successfully? Another thing is to get our software to the point where we can guarantee these 10 to the minus fifth, 10 to the minus seventh failure rates. We'll need to make sure we can comply with this DO 178B/C document. And to do that, simulation is going to be increasingly important. Just about every SUAS manufacturer has a good simulator where they can run a lot of tests on their software, but there's a lot of work that could be done, in particular with regard to analytical redundancy that Demos has talked about before. Also, you're going to see a lot of, so autopilots and SUAS are fairly new. A lot of them have some basic documentation. What you're going to see as a result of this FAA process is a very accurate and very complete documentation process where you go out and you buy a system, you're going to get handed a 300-page document on how to use it. Not that anyone's going to read it, but we're going to be required to provide that, and so you'll see those kinds of things. And that's just one of the kind of from a developer's perspective, some of the things that we'll be needing to do and to make sure we comply with FAA regulations that we see coming down the pipeline. And I guess that's all I've got. Demos, back to you.
Thank you. All right, so before we head off to a second question and answer session, let's take I guess a third poll question just to see what the audience thinks. Lori?
Okay, Demos and folks, considering the implications of FAA's next-gen policy on UAS integration, how likely are you to opt for an FAA certifiable avionics-rated GNSS receiver in your navigation payload design? Again, asking if you would just select one. And we do have one runaway response here, so you can place your bets and see if you can call those results. I'll give you just a few more moments to weigh in on that. Let's take a look. Demos?
All right, so it looks like the majority are going to wait and see until more guidance comes on from the FAA. Again, it's an interesting and a conservative approach, I guess. All right, so with that, let's I guess move on here and look at some next steps. All right, so before we go on again to the last Q&A session, there's going to be the link shown here is someplace you could go to see if you want to see more information from our sponsors, and you could contact them at that email after the webinar. And also, there are a couple of questions that came in that were asking about the slides and the presentation. All of this will be posted up on the Inside GNSS website at the link shown here, including some references that we'll provide related to the subject of this webinar. I guess we are at the point where we could open up the floor for questions to the panelists. Well, the first question is going to be we'll pose this one to Ed and or Joe, either one of you can. Can you discuss what you think the GPS GNSS backup solutions for small UAS will be in the future? Joe?
Joe here. I think some of this was discussed, and I think going forward, we're going to be seeing what we call a multi-sensor integration approach. Really anything that can be used as a source of information to provide position or relative position or velocity information will be integrated into some sort of autopilot or some sort of computer that will automatically take this information, and when one sensor disappears, it will come up with the best solution. And when you think about it, you have all these wonderful sensors on board that will be used for mapping and surveying. There's a lot of information that you can glean from that can be used to control your position drift. So if you lose GPS, you might not have your absolute position anymore, but you can certainly constrain where you are. If you're looking at the ground, you can at least stop. If in case of a helicopter, you can hover, or if in case of an aircraft, you can loiter. So I think really the future is all about multi-sensor integration.
Right. I probably could add to that also today's modern centimeter level GNSS receivers are tracking multiple frequencies from multiple constellations, and that is going to help us. We can having different frequencies to compute solutions from will allow us to do some receiver integrity monitoring that we may not necessarily be doing today, but in the future we will be able to definitely improve our integrity using multiple solutions from multiple constellations.
Thanks. All right, let's see. Next question. Let's see. This one is going to be for Josh. And what is the status of UAS avionics certification? How will an autopilot be certified? GNSS, AHRS, how will all that be certified? Do you have any thoughts on that, or is that something too early? Are you thinking about it, or what are your thoughts?
So I certainly have some thoughts on that. I don't know how this is going to go down. So it will certainly need to be. So an autopilot will certainly need to be certified in its standard operating environment with GNSS available, and that will need to be a gamut of tests with GNSS available, and just about everything else that could possibly fail will need to fail. And I imagine that will need to be part of, if not the major part of, the certification process for certifying an autopilot solution when GNSS is available. Now, when GNSS is not available, you kind of fall back to your AHRS solution, which is your Attitude Heading Reference System, where that solution also will need to be, in a similar sense, you'll need to have a test where GNSS is not available, your plane's up in the air, or your UAV's up in the air. How does it behave when everything else is working properly, and then you start dropping off all your other sensors? And you want to see, or I imagine what the FAA will want to see, is a graceful degradation in the sense that not one component will lead to a catastrophic failure. Rather, as components fall off and start to degrade or fail altogether, you'll see a kind of predictable trend in behavior that just goes down, and eventually the plane will end up on the ground. But that's kind of, those are my thoughts on that question. I hope that answers it.
Thanks, Josh. Let's see. All right, so this one is for Kelly. Again, let me get my bearings straight here, and it has to do with the current permits out there. And I don't know if you have your finger on this data, but I'll ask it, and if you don't, you don't. But the currently permitted aircraft to fly in the U.S. airspace, what is the distribution on sizes? Do you know, how many of them are big, how many of them are small UASs, and so on?
I can't give you particular statistics, but I can say that there's quite a range flying, actually, and some of it depends on who's doing the flying. Certainly, Department of Defense and Homeland Security are flying some very large platforms that we hear about. But there's also state universities and law enforcement, especially, flying some smaller platforms. So there's a range of things flying today, and I'm wishing I had a chart that showed that distribution, because I really think that's an interesting question.
It definitely is. All right, let's see. Next question. I think this could go for, well, I'll pose it to Josh for, actually I'll pose it to Ed first, and then I guess Josh could jump in as well. And it has to do with, let me go with Josh first, and then I'll let Ed also answer it. It has to do with vibration on small UASs, and how much do you see normally, and how does this affect sensors like accelerometers and gyros, and do you see them saturating?
Sure, yeah. So you definitely see vibration on small UAVs. It's a definite issue. Now, the frequencies that you're talking about typically are motor induced by, if you've got an airplane, you've got a single motor or maybe two. If you've got a multi-rotor, then you could have, upwards of 8, who knows, 12 motors all spinning at some high RPM, providing a really nice, noisy environment. Now, the frequencies, like I said, they're typically fall in some range, but the amplitudes of that noise, they're not in danger of saturating the accelerometers used on board. The accelerometers typically can handle upwards of 300 Gs, right around there, and the noise you're seeing from these motors, or on board, I guess, is not even a fraction of that. So you definitely see a lot of noise that affects the attitude solution, could affect the attitude solution, but typically does not run risk of saturation.
Joe and Ed, anything you want to add? I mean, you do make inertial systems, and what do you think of the severe vibration environment? How is that going to play?
Well, in our perspective, it's really not much difference in what we have to do in manned platforms, except that the spectrum might be different. Certainly on electrical vehicles, you don't have the induced vibrations from the engines. When we talk specifically about mapping and surveying, though, we're always of the position that why measure what you can isolate? So it's a little trickier on smaller unmanned vehicles, but if you can physically isolate the payload to some extent to not allow those vibrations to get into the sensor or the inertial sensors, then you will get better accuracy. But as Josh said, a lot of these vibrations are not high in magnitude, so it's really just understanding what you're dealing with and designing a system to handle it properly.
Right. Yeah, typically the vibrations we'd see on a small UAV are certainly not as bad as we'd see on the blade of a bulldozer or an agricultural tractor, which is where we're generally designing our equipment to operate on. So yeah, we have not experienced any problems there.
All right. All right, let's see. The next question, there are actually several of them in the same spirit, so I'll just ask one of them, and it's going to be for Kelly. And it basically has to do with beyond line of sight operations. Do you feel that they will be allowed in the future? And what's the thought process along along those type of operations right now with respect to the rules you're looking at?
I absolutely think that beyond line of sight operations will be allowed in the future. And actually, that's one of the things covered in the FAA Modernization and Reform Act. There's a requirement in there to allow beyond line of sight operations for small UAS operating in the Arctic, and actually in part for commercial operation. So there is a mandate to the FAA to figure out exactly what's needed to allow those operations to occur safely, and then once they can do it in the Arctic, they'll be able to extend that.
Right. Thanks. Let's see. Well, there's one which I think I'll field, but I'll ask Josh and Kelly to comment on it as well, and it has to do with the use of the word drone. do you not like using that word drone, and should you not use it anymore? And my view is that removes the human element from the UAVs, and it's not a therefore it's not a very descriptive term. So I prefer the term UAV and not drones. Any thoughts on that, Josh and Kelly?
Sure, I can pipe in on that for a second. Drones, the term drone has definitely, I mean, internationally in particular, has this very negative connotation, primarily, I think, because the majority of unmanned systems out there are military. And so I think that as that tendency will shift, and I think it will, as that trend shifts towards civil and commercial use, I think that the term drone will lose kind of its punch, and I think it'll become more acceptable.
And I agree with that. And actually, ICAO has started to promote the terminology remotely piloted aircraft and autonomous aircraft to make the designation of whether you have a pilot in control somewhere or you don't. And I think using that kind of terminology is much more useful than the drone terminology.
Well, let me pose this question for Joe and Ed, and it's Planix traditionally makes integrated GNSS inertial systems for manned airborne applications. Do you see this application going into the more cost-sensitive and swap-sensitive SUAV market?
Definitely. I think you know, just the response to the poll question, the first question saying that 45% of the attendees see surveying and mapping as one of the major applications speaks for itself. So, you know, as demand comes along, then, you know, GPS inertial for mapping for small UAVs is going to go into that market segment. It really is about efficiency, and so yes, the answer is definitely yes.
Right, and the challenge is trying to get the components small enough. Today, you know, we're in the centimeter level business, and getting that into a small UAV is the challenge. But luckily, you know, technology's on our side, and ASICs and memory and antennas have all shrunk, even in the high accuracy business. And today, in a 4 centimeter by 4 centimeter size receiver, we can get, you know, less than 1 watt of power. We can get centimeter level position. We can get also, in the past, we've had additional radio links for to get that centimeter accuracy in real time. Today, we can get global corrections via L-band satellite, which is all reducing the size of the components that are going on the UAV and allowing us to get on smaller and smaller platforms as we progress.
All right, thanks. All right, there are a couple of questions along this line, so I'll try to consolidate them all, and I will pose it for Kelly, and it has to do with operator certification. For unmanned systems, what is the operator certification, and how does that fit into the whole picture you're looking at?
I'll start off by saying I'm not an expert in the people end of unmanned aircraft, but I do know that there are folks working on, whether you call it certification or qualification requirements for pilots of remotely piloted aircraft. So that will definitely be something that will be required. Now, what the specifics are of those requirements, I have no idea, but they will certainly be a certification aspect to an unmanned aircraft, just as airworthiness certification will be.
Demos, do you mind if I just add to that real quick?
Yes, you may.
Okay, so just in my experience and in the experience of my coworkers here, we often have the opportunity to go out into test environments where we have the end users kind of handling and using and operating our products. And so we get to see what these people do with them and how, so in what we've seen, operator error is by far the #1 reason for crashing an unmanned aircraft. That results, or anything that results in the loss of it, whether it just flies into oblivion or, you know, operator error is huge on our list, and which is why there's, you know, divisions or scads of companies dedicated to developing more intuitive user interfaces that require less training, that make more sense to the operator to reduce that number of incidents associated with the operator error.
All right. Well, here is another question for you, Josh. And again, I'm consolidating because there have been several of them along this line. And it has to do with operating in GNSS denied environments or environments where, say, you're under trees and you're not seeing GNSS signals. How do you generate bounded solutions on things like attitude? And is it possible, and how does that work?
Sure. Yeah. So the good thing is that in GNSS denied environments, it is not extremely difficult to maintain a bounded attitude solution. What that results in is an aircraft that still maintains it's still flying level, or it maintains a loiter. That the center of that loiter will drift unpredictably, and for a hovering vehicle, when it loses GNSS or flying in between buildings and it becomes unreliable, so you can maintain fairly well a flat attitude, so that now, that's not entirely true, because you will see drift in position to the point where you may, unbeknownst to yourself, without any additional sensors, you may fly right into that tree or fly right into that building, not knowing that you're coming that close to it. So there are lots of tricks out there, mathematically speaking, to maintain that solution for as long as possible, I should say, in the presence of no GPS signal. So I don't know, did that answer your question?
I hope it answered. It was clear for me, but I'm hoping that there's a lot of questions along those lines that came in. I guess Joe or Ed, would you like to add to that? Again, seeing it from the other end, from your products where you have INS GNSS integrated.
What Josh said is bang on. If you lose GNSS and you have inertial, you can go to an AHRS mode and maintain your attitude and heading, and your position, of course, will drift as the inertia errors build up. And that goes to the comment earlier. If you have other sources of position or velociating, you can minimize that position drift. But the orientation accuracy is pretty much well established as long as you have an IMU.
All right. And well, it looks like unfortunately we're running out of time, and we have lots of questions we could have gone through here. So we apologize if we didn't answer all your questions, but at the sake of time, we have to, I guess, wrap up at this point. With that,
Demos, I can take it from here, and
okay,
yeah. So, folks, it is about that time, and I would like to wrap things up by inviting Joe Hutton from Planix Corp to leave us with a brief word. Joe?
Well, thank you. I, for one, think that was a very excellent start to trying to understand where UASs are heading, especially for commercial applications. I think it's a very difficult topic, a very complex topic, and I think the two panelists today really shed some lights on some very important things. Just for those of you who don't know, Trimble offers a complete line of products and solutions for unmanned systems. These range from small, precise position components for precision landing to GNSS inertial for mapping and surveying, or continuous position for guidance of robotic vehicles, all the way up to even a complete turnkey UAS for precision survey. As I mentioned earlier, the poll results kind of speak to themselves. 45% of you think mapping and surveying is going to be a dominant application going forward, and we've recognized that, and we believe that we have the products and the solutions and the knowledge depth to support that. So thanks again to our panelists, Kelly, Josh, and Thomas. And I would like to thank the Inside GNSS team for putting on what I think has been an excellent webinar. Thank you.
Well, thank you, Joe. And folks, before we sign off, we would like to take a moment to thank you for joining us and trust that you found today to be of value. Another very special thanks to our speakers, Josh and Kelly, and our sponsor and co-host, Trimble and Inside GNSS. As mentioned, you will see a survey at the end of the webinar, so if you take a moment to fill it out, we would appreciate it. Would also like to say thank you to our logistics producer, Patty Van Hooser, for her behind-the-scenes collaboration and support. And again, a copy of today's webcast will be available for download, and you'll receive it in the way of a link via email early next week. Most importantly, thanks for joining us. This is Lori Dearman saying have a great rest of the week. Bye for now.